Hi everyone and welcome back to Matthew Mister. Today we're going to do a chemistry Regents review on periodic trends. So to start off, in the periodic table, we're going to look at electronegativity, ionization energy, and the atomic radius. Electronegativity is the attraction to the electrons, or the valence electrons. Ionization energy is the energy needed to remove an electron, and the atomic radius is the size of the atom. So if we look across a period first, electronegativity and ionization energy are actually going to have the same pattern. So period refers to the horizontal, while groups refer to the vertical. So across a period, electronegativity and ionization energy is going to increase. Let's talk about why. Well, as we move across a period, we can see that the atomic number increases, and the atomic number is the same thing as the number of protons. And the number of protons is associated with something called nuclear charge. And nuclear charge is the total positive charge in an atom's nucleus. And we know that protons have a positive charge. So as we move across a period, this nuclear charge is stronger because each atom has another proton. And now that it has a stronger positive charge within the nucleus, it's going to have a stronger force of attraction. Therefore, electronegativity is going to increase across a period. Now, ionization energy is also going to increase because if there's a stronger nuclear charge, it's going to be harder to remove an electron. However, atomic radius across a period is going to stay the same because each period is equivalent to something called its shells. So let's take a look at lithium. I'm going to do a Bohr model on lithium. So lithium is in period 2, so that means that it has 2 shells. 1, 2. Now there is a rule regarding how many electrons should be in each shell. But first, let's look at how many valence electron lithium has. Since lithium is in group 1, that means that it has 1 valence electron, so that's going to be on the outside. And lithium in total has 3 protons, and since every element in the periodic table is neutral, the number of electrons is exactly equal to the number of protons. And since we already have one of the 3 electrons that we need, we know that we're going to have 2 electrons in the most inner shell. But a quicker way you could have done this is that if you know the rule between the energy levels, you know that the first energy level or the first innermost shell is going to have 2 electrons. The second shell is going to have 8 electrons, and the third is going to have 18. So that's the standard. That's the maximum. That's the maximum amount of electrons that you should have in each shell. Now back to my point. Since lithium is in period 2, that means that it has 2 shells. But that also means that every other element that's found in period 2 has 2 shells. So its atomic radius is going to be the same. But now down a group, electronegativity and ionization energy is going to decrease. Because as we move down a group, we can also see that the period number is increasing. And when the period number increases, that corresponds with the number of shells increasing. So as the number of shells increases, the valence electron on the outer is going to be less attracted to the positive nucleus because of something called the shielding effect. The inner electrons are shielding the valence electrons, weakening the attraction and making it easier for these valence electrons to interact. Or therefore, a weaker attraction signifies it has a lower electronegativity, making it easier to remove the electron. However, since the number of shells is increasing, so the atomic radius is increasing. One last thing we should talk about before we actually get into the questions is bond polarity versus molecular polarity. Bond polarity refers to the unequal sharing of electrons between 2 specific atoms. So this is mostly in covalent bonds, while molecular polarity focuses on the uneven distribution of electrical charge across an entire molecule. So in a covalent bond, you have a nonpolar covalent bond versus a polar covalent bond. So nonpolar means that 2 atoms have identical or very similar electronegativity. So the pull between electrons is mutually balanced, and the electrons are shared equally. But a polar covalent bond, when there's a big difference or a medium difference of electronegativity between the atoms that are sharing the electrons. So the more electronegative atom is exerting a stronger pull, causing the shared electrons to spend more time closer to the nucleus. So the more electronegative atom develops a partial negative charge because it's attracting more of the electrons, while the less electronegative atoms develops a partial positive charge. And this separation of charge is called a dipole. And this symbol here represents partial charges. Now, bond polarity, which is between the inner bonds of the molecule, is going to impact the overall polarity of the molecule itself. But most of the time, when we're comparing molecular polarity, we're actually looking at the geometric shape of the molecule. So a nonpolar molecule is typically symmetrical. For example, if we look at CO2, we have C and then double bonds with O, and it's clearly symmetrical on both sides, making it nonpolar. But I also want to note something between the inner bonds, the bond polarity. Now, while the entire molecule of CO2 is nonpolar, if you look at the individual bonds between oxygen and carbon, the CO bonds are polar because oxygen is more electronegative. But because, again, all of CO2 is linear, the effects are going to cancel out. The partial charges are going to cancel out. And the shape is going to be symmetrical, making it nonpolar. But a polar molecule is asymmetrical. So for example, if we take H2O, we have oxygen, then we have hydrogen. If we look at the individual bonds, OH are very polar because oxygen is more electronegative than hydrogen, and because H2O has a bent shape, it's asymmetrical and therefore polar. Also, partial charges are developed where, since oxygen is more electronegative, it's going to develop a partially negative charge, and the hydrogen is going to develop a partially positive charge. And it's the same scenario for CO2. Since oxygen is more electronegative, it's going to develop a partially negative charge, and carbon is going to have a partial positive charge. Question 1 says state environmental agencies are studying the properties of gases found in residential settings. Methane is a common fuel gas used in older home appliances, but it is being phased out in new construction due to environmental impact and indoor air quality concerns. Methane features single polar covalent bonds between carbon and hydrogen atoms, allowing it to burn easily. To find safer alternative materials, engineers map out the chemical bonding patterns and properties of several candidate gases. The table below displays data for 4 different gases. So first of all, we have H4, we have methane. And it says it features a single polar covalent bonds. So we have single polar covalent bonds. So if we actually sketch it out, methane is going to look like this, where we have single polar covalent bonds between carbon and hydrogen. Now the question is saying which gas from the data table has chemical bonding patterns and structural properties most similar to methane, the fuel gas being restricted in new residential stoves and furnaces. Well, the text told us it's single and polar covalent. So if we look at the type of bonds, we can eliminate 2 and 4 because these are nonpolar, and we can eliminate 3 because even though the type of bond is the same, this one says it has 6 bonds, but methane has 4 bonds. 1, 2, 3, 4. So the answer is 1. Question 2. Modern cookware is often coated with ceramic to make it scratch resistant. These coatings are made by soaking glass in a hot liquid bath containing lithium ions. The lithium ions replace the original sodium on the glass surface. Because these ions are different sizes, which causes the surface atoms to pack together more tightly. Which statement describes why positive ions in the hot liquid bath can easily replace the sodium ions on the surface of the cookware glass to make it stronger? Well, we are between A, B, C, and D. In the question, we're talking about lithium ions and sodium ions. But C and D are talking about silicon, which is not relevant. So now we're between A and B. Let's read A. A is saying that sodium and lithium have similar patterns of electrons in the outermost energy levels. So this is referring to valence electrons. If we look at the periodic table of elements, we see that lithium and sodium are both in group 1, meaning that they both have one valence electron. So this is true. But then it says they have the same number of occupied energy levels. This refers to the shells. But this is not true because lithium is in period 2, so it has 2 shells, but sodium is in period 3, so it has 3 shells. So that means that it does not have the same number of occupied energy levels. But B is going to be right because yes, they do have similar patterns of electrons in the outermost energy level, but sodium, Na, has more occupied energy levels than lithium because it's in period 3. It has an extra shell. Now question 3. So here we have a table with different elements and information on their atomic period, number of occupied energy levels, and pattern of electrons in outermost energy levels, and reactivity with oxygen. Now the question asked, identify the name of element A based on the pattern shown in the data table and explain why. Element A says that it has an atomic number of 7. And the atomic number is like an ID badge for the atoms because the atomic number is the same thing as the number of protons. And we know that each element in the periodic table is identified through their atomic number. So the element that has an atomic number of 7 is nitrogen. So element A is nitrogen because it's identified through its atomic number of 7. Question 4. Which statement correctly compares the patterns of electrons in the outermost energy levels for element A, phosphorus, and element B? So again, electrons in the outermost energy level refers to valence electrons. If you look at the table, patterns of electrons in the outermost energy level, patterns of electrons here. Element A, phosphorus, and element B. They all have the same amount of electrons. So they all have the same amount of valence electrons. So that means that they're all found in the same group. So let's read A. They all have 5 electrons in their outermost energy level because they are on the same period. That is not true because the period corresponds with the number of shells, not their valence electrons. B says they all have 5 electrons in their outermost energy level because they are in the same group. This is true. So the answer is B. Based on the data table, describe the trend in chemical reactivity that group 50 elements have with oxygen as the number of occupied energy levels increase from 2 to 4. Well, in the previous question, we identified that element A was nitrogen because of its atomic number. Now, if we want to identify element B, we look at the atomic number, which is 33, and we can find that it's arsenic, and arsenic is also in group 15. So nitrogen, phosphorus, and arsenic are all group 15. So now that we know that information, the question is asking, describe the trend in chemical reactivity that these elements have with oxygen as the number of occupied energy levels increase from 2 to 4. So if we look at the occupied energy levels, it goes from 2 to 4, and it's asking for the reactivity with oxygen. We can see that as the number of occupied energy levels increases from 2 to 4, the reactivity with oxygen is also increasing because it's going from low to high to medium, so it's increasing. Question 6. Identify the total number of occupied energy levels in a neutral ground state atom of a traditional propellant xenon. Well, if we look at the table, it tells us that xenon has 5 occupied energy levels. So the answer is going to be A. State the relationship between an element's vertical column on the periodic table and its pattern of electrons in the outermost energy level, using group 18 elements from the table as evidence. Well, we know that the vertical column refers to the group, and that the group number identifies the number of valence electrons. And if we look at group 18, this means that all of the elements in group 18 have 8 valence electrons. So we can say that elements such as argon and xenon, which are in group 18, are going to have the same amount of valence electrons, which is 8 electrons, because they're found in group 18. Question 8. Based on the graph, what is the pattern of ionization energy across period 3 from left to right? Well, if we look at period 3 includes elements with an atomic number ranging from 11 to 18. So we're looking from Na to somewhere around here, before 20. We can see that the ionization energy is steadily increasing. The reason being is because as we move across a period, the nuclear charge is strengthening the force of attraction, therefore making it harder to remove electrons. So it's not going to go down, it's not going to stay the same, So we can eliminate A and D. Now between B and C, it says it goes up because the number of outside electrons decreases. That is not true, because across a period, the group number is also increasing, meaning that the number of valence electrons is actually increasing. So it's not B. So the answer is going to be C. It generally goes up because more protons in the nucleus pull harder on the same outside energy level. So this is true because they're all in period 3, so the energy level is going to stay the same, and the nuclear charge caused by the increased amount of protons is going to strengthen the ionization energy. Last question. Based on the patterns across period 3, explain how an atom's physical size or atomic radius changes its ionization energy. In your answer, use what you know about how the positive nucleus pulls on the outside electrons. Well, we know that the atomic radius is going to get smaller across a period because the nuclear charge is getting greater. And because of that nuclear charge, the smaller atoms with the smaller atomic radius is going to require more energy to remove an electron, making the ionization energy higher. That's it.